So today I'm going to talk about the various states of a fluid or the states of a material. And what I mean by state, I mean is its physical state. So let's just look at an example. Let's look at water. So water can exist in three common different states or phases, and we're all familiar with these. We've encountered them all the time. So the first is a solid, liquid, and a gas. And so solid would be ice cubes, and then liquid would just be regular old water that we pour out of our tap. And then finally gas, or also known as steam. Sometimes we refer to gas phase water as steam. And at 1 bar, or 1 atmosphere I should say, 1 atmosphere, which is almost 1 bar, almost equivalent to 1 bar, but at 1 atmosphere, the boiling point for liquid water is 212 degrees Fahrenheit. The freezing point is 32 degrees Fahrenheit. So if we are below 32 degrees Fahrenheit, we will have at 1 atmosphere, we should start to form a solid phase for water. If we're above 212 degrees Fahrenheit, we should start to form a vapor or a gas. Vapor is just another word for a gas, but a vapor, gas, or often what we also call steam. Somewhere in between those two temperatures, we should have liquid phase of water. And so that's just an example of the different phases or states of water. And this again, these temperatures are at 1 atmosphere. If I were to take the pressure and I were to increase it dramatically, say from 1 atmosphere to 200 atmospheres, if I change that pressure, then the boiling points and the freezing points may change. So they're not necessarily fixed to 32 degrees Fahrenheit or 212 degrees Fahrenheit. It very much depends on the pressure at which I'm operating at. So I have here a phase diagram. This is a pressure temperature diagram, and what it shows us is the different phases of a material depending on the pressure and the temperature. So if we're in this region of the diagram, we are a solid. If we're up in here, we're liquid, and down here in a vapor. And again, it depends on pressure and temperature. So let's just say that this is 1 atmosphere. This diagram is by no means exact. If you want an exact diagram with numbers and everything, Google it online, whatever, and find something exact. But this is just for illustrative purposes. But if at 1 atmosphere, if I were to come across here and look at that transition between solid and liquid, that would be right here at 0 degrees Celsius. So that's the freezing point of water. If this was a phase diagram for water, and then if I were to go ahead and follow this diagram out here at the point where it touches the line right there, that would be at 100 degrees Celsius, and that would be the boiling point of water. And then it would go from liquid phase up here at 1 atmosphere, and then come over to this region as we go up to higher temperature into the vapor phase. And of course this was an example for water, but these exact numbers will depend on the material that we're looking at. So for instance, carbon dioxide at room temperature, it is a gas. So it's very much in this region down here at room temperature and at 1 atmosphere, whereas for a liquid material like water at room temperature, it's in this region at 1 atmosphere and room temperature. So whatever the exact numbers are and where these lines align, where these lines are, very much depends on the material we're studying. And some materials at room temperature are liquids, some materials are vapor, some materials are solid. It just depends on the material. So let me draw another phase diagram, and this is using alternate parameters or properties, but this is pressure here on the y-axis, and this is specific volume on the x-axis. So it's not volume, but it's specific volume, meaning it's volume per amount of material, so it's volume per mole. So it's actually the inverse of density. And the specific volume could also be volume per mass, volume per kilogram, but in this example I'm just showing it as volume per mole. But it's the amount of the volume per mole or per amount of material. And this diagram here shows us the various phases of a particular material. So in this region we have liquid, this region we have vapor, and in this region we have vapor plus liquid. And so this region right here in the middle, this is a mixture region. So it's a place where we have different phases in contact with each other and in equilibrium with each other. And the best example I can give you of this is boiling water. So if you put on your stove some water, put it on a pot, turn it on, eventually it'll start to boil. And what you'll have above your pot is you'll have vapor gases coming in of steam, of liquid water that's boiling into the vapor phase, forming, and it's evaporating into the gas phase. But you'll also have some water, liquid water, left in the pot itself. So you have the steam coming off of the liquid, and then you have the liquid still in the pot itself, and they're in equilibrium with each other. So that water that originally you started with is a mixture of vapor and liquid. So what I've added onto this diagram are lines of constant temperature. So these are lines at constant temperature. So this right here, this line right here represents one specific temperature. This represents another specific temperature. And again, with this whole diagram, I haven't added any specific numbers to it. This is just the general shape or properties of these PV diagrams. And so what this tells us is that if we are at a given temperature, say along here, as we're going from over here, the vapor phase, over to the liquid phase, this whole process going from vapor to liquid or liquid to vapor and going through this mixture phase right here, this is at constant temperature. So this process, boiling, is a constant temperature process, and that's what we say when we say the temperature is 212 degrees Fahrenheit or 100 degrees Celsius for boiling of water. That's because this whole process of going from liquid to vapor is at constant temperature, but there's this transitional region where we have both vapor and liquid as we're going from one to the other, but it's all at the same temperature, which is the boiling point of that particular temperature. So what I show you here is just, again, another alternative way to show the different phases, liquid and vapor, and the transition between the two. In this case, it's showing here on the y-axis temperature versus this specific volume. Again, liquid phase over in this region of this map, region over here we have vapor, and inside this region, inside the curve, we have the mixture of liquid and vapor. So let me just give you a few more details. The technical term for this region up here is known as a subcooled liquid. So if we're ever in the region where our temperature and specific volume is in this region, it's a subcooled liquid. There's a corresponding region on the pressure volume chart, but we're just looking at the temperature volume chart right now. But anyways, this is subcooled liquid. This region right here is known as a saturated vapor. If we are on this line, this black line here, which is the separation between the liquid and the mixture region, that is known as a saturated liquid. And on this side, it's known as a saturated vapor. So you can think of saturated liquid as completely being liquid, but almost right to the point where some of that material is going to vaporize, or some of it's going to boil. So we don't quite have any vapor or gas phase, but we're so close that if we just wait one infinitesimally second longer, we're going to go into the mixture region, so we're on the line. Same thing goes over here. If we have a saturated vapor, we're 100% vapor, but we're so close to condensing some of that vapor to make a liquid that we're almost to the mixture phase, but not quite. Right on the line there. And this is, again, the phase diagram that illustrates the different types of materials we have. And again, let me just emphasize that if we know the temperature, the pressure, or the volume, we need to have two different parameters. And once we know those two parameters, we will define the state, whether it's a subcooled liquid, a mixture, or a superheated vapor. And the other thing that's unique about this line is once we know what our temperature is on this line, we instantly know what our pressure is. And so at any point on this line here, we have the saturation pressure and the saturation temperature. So once you know a saturation temperature, you also know the saturation pressure and vice versa. They're paired together. Saturation pressure and saturation temperature are paired together because of the line. There's only one unique way that you can be on this line, on these lines here, at a given pressure or temperature. And I haven't shown you one last part about this. So let me just see how this all fits together. There are constant lines of pressure, and we saw this on the pressure volume diagram. But in here, if I have the temperature versus volume or specific volume, these lines right here represent constant pressure lines. So this is a temperature at a given, or this is a one given pressure. This may be 1 atmosphere. And this region where we go across here is in a horizontal line. So when we're going from a saturated vapor to a saturated liquid, the pressure stays constant. And I just want to make sure that this is illustrated here on the diagram so that you can see that. The energy it takes to go from right here, this point, a saturated liquid, to a saturated vapor, that's the latent heat of vaporization. That's the energy it takes to boil the material, going from here all the way over to here. And that process is a constant temperature, constant pressure process going from here to here. Same thing if we were to follow a different constant pressure line. So the last concept related to mixtures and the phase is how do we actually get the energy of a mixture. So we can look up, for instance, on steam tables and other tabulated data, we can look up the energy of a liquid or a vapor. But what do we do about when we're in this region right here where we have a mixture of both liquid and vapor? Well, we define for a mixture XV and XL. XV is just the fraction of vapor. What fraction of our material is a vapor? And that can be between 0 and 1. 0 being no vapor, 1 being all vapor, and then some number in between, like 0.5, meaning we're essentially 50% vapor, 50% liquid. XL is the fraction of liquid, which is just 1 minus XV. If we know these values, we need to know these values in order to find out how much energy is of that mixture. So the formulas for calculating out the energy or thermodynamic properties of a mixture are pretty straightforward. The internal energy of this mixture, containing both liquid and vapor, is equal to the fraction vapor times the internal energy of the vapor phase, plus the fraction liquid multiplied by the internal energy of the liquid phase. So what are these UVs and ULs? Well, first off, these all have these little bars overhead to remind us that these are internal specific quantities. So this is energy per mole, or energy per kilogram. It's the amount of energy per amount of material that we have. So this units of this could be, for instance, kilojoules per mole or kilojoules per kilogram. But in any case, this number right here, UV, is simply the energy of the saturated vapor. That would be the energy somewhere along this curve right here. This energy here is the energy of the saturated liquid. So that's the energy for somewhere along this curve right here. We can look up these values in tables, tabulated data. For instance, the steam tables, which we're going to get an opportunity to use, they have all the energies for saturated liquids and saturated vapors listed in the steam tables. The equations for the mixture, an enthalpy of a mixture, very similar. It's just the fraction vapor multiplied by the enthalpy of the saturated vapor plus the fraction liquid multiplied by the enthalpy of saturated liquid. The volume or specific volume is equal to fraction vapor times the specific volume of saturated vapor plus the fraction liquid multiplied by the specific volume of the saturated liquid. And again, all these values here are tabulated for common materials such as water, which we're going to deal with a lot in this course. And so that's our basic introduction to the various phases of materials. And we're going to work with different phases of materials. We might deal with, for instance, water. We might deal with other materials, but we're going to have to be familiar with these concepts. So if you go through this video and things are a little unclear, fuzzy, just review the video again or ask questions in class or ask questions on the discussion board or whatnot.